All right, this is the answer key to the practice test, starting with limits algebraically. So this is covering the three strategies we talked about in class. Number one is direct substitution. So I'm going to briefly cover this. Number one, we have direct substitution, which is what you want to go to as kind of a default. Substitution is just plug in the value. Substitution. Okay, substitution. Good. All right, so the first one, hey, I just plug in 2. So we're going to say 2 squared minus 2 plus 1. That's 4 minus 2 plus 1. That is 3. That's it. So these are the easy questions, right? You're just plugging in the value into the function. 2 times 1 plus 1 over 3 times 1 plus 1. That is 3 over 1, which is 3. Again. Okay. Again, just plug in the 1 for x. Square root of 10 times 1 minus 1. That is 10 minus 1, which is 9, equals 3. Okay. For this one, same. Plug it in. 1 squared minus 1 minus 2 over 1 minus 2. That's 1 minus 1 is 0. Minus 2, that's negative 2. 1 minus 2 is negative 1. We have negative 2 over negative 1. That is 2. Okay. So here's with the transitions. These are all easy direct substitutions, well, relatively. And then this is where we change. So let's try direct substitution just to check. We would have 2 squared minus 2 over 2 minus 2. So that's 4 minus 2 is 0. And then 2 minus 2 is 0. So this right here is a danger zone, right? This is indeterminate. Essentially, it means unknown. We don't know. Indeterminate. Okay? So since it's indeterminate, we want to revisit our original function and see how we can simplify in some way. And the first method, so this is, if we think about after direct substitution, you want to think about factoring. Factor. So the denominator here is fine. Like I can't do anything with x minus 2. The numerator x squared minus x minus 2. Again, if you want a method, you want a number that multiplies to get the negative 2. Don't forget the negative, and adds to get the negative 1. That would be negative 2 and 1. So these are two values that work. So my factors are x minus 2 and x plus 1 over x minus 2. Notice we have a hole here at x minus 2. These will cancel. And so we'll have just x plus 1 left over. So now I'm going to take the limit of this I'm going to basically bring this back. We're going to take the limit as x approaches 2 of x plus 1, which is direct substitution 2 plus 1, which is 3. Okay, so again, indeterminate value, go back to the function, simplify by factoring, cancel, and then find the limit of what we have left over. Next one. So this one, okay, if I plug in 4, I'll get 2 minus 2 is 0, 4 minus 4 is 0. So you're going to get you're going to get indeterminate when I plug in 4, which I don't like. Also, factoring looks challenging. There is a way to factor this. We haven't really gone over that yet, so I don't want to talk about it right now. But I do see here the square root in the numerator. And based on what we went over on Wednesday, this is where you want to use the conjugate. So I suppose this would be after factoring. You might want to consider multiply by conjugate to cancel out the the square root. Okay, so the conjugate, you want to multiply by the conjugate of the square root value. So my square root value is in the numerator here, so I'm going to multiply by square root of x plus 2 over the square root of x plus 2. Remember, this is just multiplying by 1, right? I cannot have different values in the numerator and denominator. We're multiplying by 1. I'll show you, so the numerator we're going to multiply. Let me show you like what's going on here. So when we multiply by root x plus 2 and root x minus 2, root x and root x just become root x. 2 times root x is 2 root x. And then this is negative 2 root x. And then 2 times negative 2 is negative 4. So what happens is the 2 root x and the negative 2 root x cancel. So all I have left is x minus 4. Okay, so back up here, this equals x minus 4 over what now I'm not going to multiply these two together. I'm going to leave them as they are. So x minus 4 over x minus 4 times root x plus 2. Now, can I cancel? Yes, I have a whole here at x minus 4. So now it drops down and I have 1 over root x plus 2 remaining. I'm going to take the limit of this now as x approaches 4. And that will get me 1 over root 4 plus 2, which is 1 over 4. Okay, so again, similar pattern. You try and solve it with direct substitution, doesn't work out. Then you multiply it by the conjugate, top and bottom by the conjugate to cancel out that root x. Remember, you only need to multiply it by the numerator, or in this case, the numerator, because that's where you're canceling out. The denominator, you leave them like this. Cancel the whole, then plug it in. Okay. 3 more to go here. So again, this is similar. Negative 3 squared is 9. So this is 0 over 0. I can see when I plug in negative 3. So let's factor this. This is a difference of squares. X squared minus 9. We need to get used to seeing this. X squared minus 9. Again, if you're solving this traditional way, you would do two numbers that multiply to get negative 9 and add to get 0. That's 3 and negative 3. Again, you're just going to get used to seeing this all the time. This is a difference of squares. This is x plus 3, x minus 3 over x plus 3. The plus 3's will cancel. And we will just have left over x minus 3. Then we'll take the limit of that. Limit x approaches negative 3 of x minus 3. Through direct substitution, this becomes negative 3 minus 3, which is negative 6. Okay. Next one. So that's 0 on top when I plug in negative 3. This one, negative 3 squared is 9 times 2 is 18. Plus 3 is 21. So this one is going to come out to 0. 0 over 0, I can see when I plug in negative 3. So let's factor again. So I just factored this to the left, x squared minus 9. So I don't need to do that again. I can just rewrite it. I know that is x plus 3, x minus 3. And then the denominator. This is a more challenging factor. We have 2x squared plus 7x plus 3. We cannot do the diamond method. So this method here, I cannot do because of this 2, right? And also it doesn't seem like I can take out a common factor here. Like nothing goes into all 3 of these values. So what you do, or what I do, is make my box. And I know that when I factor this, I'm going to have to get 2x plus something times x plus something. Okay, the reason I know that is because the only way to get 2x squared is 2x and x. So this is going to be 2x here. This is going to be an x here. So that's 2x squared. And I know they need to multiply to 3. And the only way to get 3 is 1 and 3, right? But I need to get them to add to 7. So I put a 3 here and a 1 here, plus 1 plus 3. 3 times 2x is 6x. X times 1 is just x. This is it. When I add these up, I'll get this. 2x squared plus 7x plus 3. So we got 2x plus 1 and x plus 3. So that goes back up here. 2x plus 1, x plus 3. Again, cancel. And now I have x minus 3 over 2x plus 1. Let's go ahead and take the limit again. Negative 3 minus 3. Negative 3 minus 3 equals negative 6. And then negative 6 plus 1 is negative 5. So we have 6/5. That's the limit of this problem. Okay. Last one. This is another conjugate. I know it's conjugate because of the square root. So I'm going to multiply top and bottom by square root of x plus 3 over square root of x plus 3. And I know what that's going to get me based on what I know about conjugates and what I showed you earlier. That's going to just get me x minus 9 here. And on the bottom, we're going to leave them as factors, x minus 9 and root x plus 3. Cancel. So we have 1 over root x plus 3. We're going to take the limit as it approaches 9. That becomes 1 over root 9 plus 3 because I'm substituting in that 9, right? That 9 is going in to x, and that is 1 over 6. Okay. So kind of like 3 types of problems. You have just the regular direct substitutions, you have the factoring, and then you have the conjugate. So you need to know all 3 for the test. Okay, factoring, direct substitution, and conjugate. Okay, last one here, or last one, the first page. We're at the following sigma notation. So sigma notation, review, we have this symbol, this is the sigma, and you're going to have an index, meaning a starting point here, and an endpoint here. And here we have what's called the argument, which is our function essentially, okay, what we're doing each time. And you're going to add all these values together. So a good place to start is just looking at it. We have 8, 15, 22, 29, 36. How many values do I have? I have 5. So let's make 5 terms. If I put a 1 here and a 5 here, that means I'm going to have 5 terms. 1, 2, 3, 4, and 5. I mean, I'll kind of show you what that looks like. 1, 2, 3, 4, and 5. These 5 terms here. Okay. So we're going to add these 5 terms together. Okay. Now, what's happening here? So we're doing 8 plus 7 is 5, plus 7 is 22, plus 7 is plus 7 every time. So if my rate of change is 7, then I want to be adding 7 for every x, just like a linear equation. I'm adding 7 for every x, right? And then my starting point is 8. So if you imagine for my first term here, I'm going to plug in, it's going to be like 7 times 1. Then my next term is going to be 7 times 2, then 7 times 3, then 7 times 4, then 7 times 5, right? But see, I want to start at 8. So if I want to make this start at 8, I need to put a 1 in front. Because when I have a 1 in front, then that'll become 8. 1 plus 7, this is 8. 1 plus 14 is 15. 1 plus 21 is 22. And 1 plus 28 is 29. And 1 plus 35 is 36. So my advice is to always test your summation. If you think you got the right one, test it. Plug in 1, plug in your indices, right? This is 1, 2, 3, 4, and 5, and see what you get. I do get 8, 15, 22, 2936. Okay, number 3. We have a graph to our right showing a function, and we're being asked, is the function to the right continuous at x equals -1? Explain using the formal definition. Okay, so before we get into the formal definition, let's take a look at our graph. Let's go to -1, right? This is x equals -1 right here. And I can see, yeah, looks pretty continuous here. We have a straight line going through this. There's no hole, there's no asymptote, but looks good. That's x equals -1. Okay. So I would say yes, right? Yes. Right. This is 1 point, this is like half a point at best. We got to use the formal definition of a limit. And if you remember, the formal definition of a limit is 3 parts. And you need to know this, you need to memorize this. Number 1, limit exists. Okay, simple. Number 2, function is defined. That means essentially no. That means like no hole / asymptote. Okay, and then 3, limit equals function output. Okay. In mathematical notation, let's prove this, right? So limit exists. Well, I can see here that the limit, we know a limit exists when the limit, so also you need to know this, the limit from the left equals the limit from the right. So the limit as x approaches -1 from the left of f of x equals the limit as x approaches -1 from the right of f of x. Okay, this notation right here, I'm showing that the limit from the left, right? This is the limit from the left right here equals the limit from the right. I'm showing that they're equal with this notation. So that's number 1. Check. This proves it. So I need to see this, right? I need to see you tell me, okay, the limit from the left equals the limit from the right. So therefore the limit exists. Okay. Function is defined. So we can see here when we plug in -1, it looks like, maybe -0.5. So I can say here f of -1 is defined, right? It's roughly -0.5. Okay. And finally, for the limit equals the output, you're just going to say limit as x approaches -1 of f of x equals f of -1. That's it. That's all you need to do to prove it. So function is defined. We can see that visually, no hole. And then the function equals a limit. That's what I'm showing here. The limit as we approach -1 equals it. However, right, if I had told you instead of doing -1, we did -3 right here, right, you would take a different strategy, right? If you did x equals -3, you would say, okay, yes, the limit exists because as we approach -3 from the left, it approaches -3 from the right, right? It's the same limit. But you would say it is undefined, right? f of -3, this is what you would say. F of -3 is undefined, right? So that is why it would fail, right? It would fail the second and it would fail the third because of that. Okay, so this would be not continuous. Okay, so x equals -3 is not continuous, but In this case, x equals -1 is continuous. All right, I'm going to kind of box this off so it's clear this is two separate things. Okay. So when you're going to get maybe something similar to this on the test, I need to see three things checked off. The formal definition. Limit from the left equals limit from the right. Defined. Limit equals the output of the function. Okay. Number 4. For what value k is the function below, and the function below does limit as x approaches 1 exist? So we haven't spent a lot of time on this in class. In fact, maybe one of my classes we haven't covered this, but this has been in your homework. We know a limit exists. Again, important information to memorize to know if the limit from x as x approaches 1 from the left of f of x, don't forget this part, f of x, equals the limit of f of x as x approaches 1 from the right. If these are equal, the limit exists. And we know to take the limit, we can use direct substitution, right? So let's now, as we approach 1 from the left, we're going to be using this function because this is for x values that are less than or equal to 1. So this is from left, okay? This is from the right because it's greater than 1. So the limits of both of these need to be the same at 1, okay, as x approaches 1. So let's plug that in. So the limit as x approaches 1 of -2x squared minus 7 needs to equal the limit as x approaches 1 of -x squared minus 2kx. Then here, we're using direct substitution. I'm going to put that up here. It's like direct sub. Okay, I'm just going to plug in the 1 for x in both. Okay, so now -2 times 1 squared minus 7 needs to equal -1 squared minus 2k times 1. And so we're solving this equation for k. Okay, so let's simplify here. So this is just -2 minus 7, right? 1 squared is 1 times -2 is -2. -2 minus 7, that's -9, right? Equals -1 squared. So 1 squared is 1. Take the negative is -1 minus 2k. Okay, following me so far? So the limit from the left and the right are the same. Since this is from the left and this is from the right, we're setting the limits equal to each other. And then we're doing direct substitution to evaluate the limit. Right? The limit as x approaches 1 of this, I'm doing direct substitution here. And I'm setting them equal to each other, and I'm solving for k. Right? K is my only variable. So now I'm at this point where -9 equals -1 minus 2k. I want 2k by itself. I'm going to continue this down here. Okay, so I'm going to go through this question. I'm going to rewrite it to just make it clear. I'm going to add 2k to both sides. It'll give me 2k minus 9 equals -1. And then I'm going to add 9 to both sides. It'll get me 2k equals 8. And then I'm going to divide by 2 on both sides. And k equals 4. Okay. So this is all one problem. Okay. So again, if that was confusing, rewind and watch out from the beginning. We set the limit equal to left and right. That's from the definition of limit. Okay, I'm moving on. Sketch a graph of function q for which limit as q approaches t from the right of qx is 2, and the limit is, which is q approaches 3 from the left, is -2. Okay. This may seem challenging, but it's not. Okay. Essentially, we have an axis that we're going to draw, and we're going to have a function called q of x. And q of x can do whatever we want, but the only important thing is that when we're at 3, let's call this 3. When I approach from the left, the y value needs to approach 2, and when I approach, from the right, it needs to approach 2, and when I approach from the left, it approaches -2. So let me stretch this out a bit, and I'm going to start my function from the left. Let's start with the left here. So I need to make sure I'm going to mark this as -2, and I'm marking this as 2. I need to make sure that as I come, my function comes. So I can do whatever I want with this function, but as it comes to 3 from the left, the limit needs to be -2, and I'm going to put a hole here. Okay, and then I'm going to draw my other function and go from the right, and as I'm approaching 3, it needs to equal 2. It doesn't matter if your filled hole is in the top or the bottom, but one of them needs to be a hole, because you can't have two values that are the same for a function, right? So I cannot have a filled hole here and here. One needs to be open. Doesn't matter which one. It just one. So this is limit from the right is approaching 2. Limit from the left is approaching -2. That's it. Okay, and you can just go back and test it if you're not sure. Okay. Number 6. We are writing a Riemann sum in sigma notation to calculate the area between 13 and 7 using 8 left point rectangles with equal width. So I think helpful here is to kind of draw a little visual. Like, you don't have to draw anything fancy. It doesn't have to be accurate in the slightest. It's just helpful to see what's going on here. Okay, so if we imagine like this is our function, it's not accurate at all, but I'm just drawing it just to show you it doesn't have to be accurate. Let's say that this right here is 13, and this is 17 right here, and I'm doing 8 left point rectangles. So that means I should have 1, 2, 3, 4, 5, 6, 7, 8. Okay, we'll call this 17 here. I'm going to move 17. Okay, so this is roughly what I'm trying to get. I'm trying to add all these up together. So really good starting point, just draw it. Draw a visual. What do you want? I should have 8 rectangles, and I should be going from 13 for 7. So like, oh yeah, I'll give you points for doing this. Okay. Now let's start setting up our summation. So sigma notation, like, you need to know what that is. That is one of these. And don't start like filling in 13 and 17. I don't want to see that. Don't start filling in 13 and 17. Let's do the argument first. Because again, this is the argument here. What are we adding, right? You got to think, let's think conceptually. We're adding rectangles, right? So rectangles are what? Area of a rectangle is base times height, right? This is area of rectangle, right? So you're adding a bunch of base times heights, right? So what's the base of each of these rectangles? That's the easy part. Well, we're going from 13 to 17. That's a difference of 4, right? From 17 to 13 is 4. And we have 8 rectangles. Therefore, 8 equal rectangles, right? So therefore, we're going to do base equals 4 over 8, which is 1/2. So the bases of all my rectangles is 1/2. This is the base. Okay. Then we need the heights. So we're trying to find all of these, like the left side of all these rectangles, right? Like the left side of all of them. Well, the height of all of them is equal to the output of the function at these x values. So at 13 13.5. I want 13, 13.5, 14, 14.5, 15, 15.5, 16, and 16.5. That is 8 rectangles, 8 heights. Okay, so I want the output. Output of the function is represented by f of, right? Now my first output that I want is 13, right? That's the first height I want, f of 13. Okay, now what's the next height I want? The next height I want is 13.5. So I'm adding 1/2 each time. 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. That's going to be x. Or you can be whatever variable you want. Right? So this right here is the height. Okay. Now we still need to do our indexes here. So where do I want to start? Well, again, you kind of want to think about this conceptually. I want my first value to be 13, right? So my first value down here, I actually don't want to be 1, because if I make it 1, then I'm going to plug 1 in here, and I'm going to get 13.5 as my first value. So I want to make it 0. 0 is going to give me the left side of the rectangle. If I made it 1, I would be looking at the right side of the rectangle. Okay? And we're going to go to 7, not 8, because 0 counts as a number, right? You have 0, 1, 2, 3, 4, 5, 6, 7. That's actually 8 numbers. And that's it. That is the Riemann sum. Okay? I mean, I can expand this a little bit just so you're seeing what's going on. This would get you 1/2 times f of 13 plus 1/2 times f of 13.5, and so on until we got to 16.5. Okay. And this f of 13, this f of 13.5, you would be plugging in 13 into this equation. I'm not asking you to do that. I'm just asking for this. This is your answer right here. Okay. To find f of 13, you're just plugging 13 into this equation, 13.5 into this equation. Okay. All right. Consider the following function defined by the graph. This is limits graphically. Okay. Let's read through it. I want the limit. Again, you gotta know how to read the notation. Limit of the function as x approaches -1 from the left. I go to -1. I'm approaching it from the left. So I go. Let's move to the left of -1 and start coming towards it from the left. As I follow my function up, I'm approaching 2. This is 2. Okay, because I'm approaching 2. Let's approach from the right. All right, I'm coming towards -1 from the right. I still get 2. All right, the next one is just the limit of -1 overall. So since the same from the left as the right, the limit is 2. Okay, how about -4? So as the limit approaches -4, notice as we approach from the left, we get 3. As we approach from the right, we get 4. So since they're different, this does not exist. You just want to take your time with these, okay? Go to the x value, work towards it from both sides of the function. If they're meeting in the middle, right? If they're high-fiving, right? Then the limit exists. If they're not, if they're missing, then it should not exist. Okay. How about regular 4? All right, we get a similar situation. If we approach from the left, right, we are getting to -3. Right, this is 4. As we approach from the right, we're getting towards -2. They're different. Does not exist. Okay. More of these. Okay. Limit as x approaches 1 from the left. So let's go to 1. We'll approach it from the left. As we approach from the left, it approaches 3. Let's approach 1 from the right. We'll go to 1. We're approaching from the right. We're still approaching 3. Okay. And so the limit overall is 3. And then how about limit of -5? So we're going to go to -5. Uh-oh, we got a problem, because when I approach from the right, I approach 3. When I approach from the left, I approach 2. Therefore, since they do not match, does not exist. As we approach 5, similar issue. Left side is 0. Right side is 1. Does not exist. Okay, 2 more problems. Given f of x equals square root of x plus 1. Sketch the graph. So if you're like panicking because you don't know how to do this, like I don't know how to do a square root function, what does that look like? Don't panic. Make a table, guys. Make a table. So you can, over here to the left, to the right, you can say, we'll do it here. X and f of x. Just like plug in some values. Use your calculator. Don't panic. Always go to start with a 0. What's happening at 0? Square root of 0 plus 1 is 1. Okay, that one's easy. How about 1? When I plug in 1, square root of 1 is 1 plus 1 is 2. Okay, that one's easy. 2 and 3 are kind of messy because they're irrational, right? Let's plug in a 4. We plug in a 4. Square root of 4 is 2 plus 1 is 3. Okay, well, I got some nice points here. Now let's plot them. So I got 0, 1. I've got 1, 2. And I've got 4, 3. I'm kind of getting a picture of this. And I know that at 9, 9 is another perfect square. Square root of 9 is 3 plus 1. That would be 4. So I know I should roughly be hitting 4 kind of over here. So let's just sketch this. It doesn't have to be completely perfect, but it's going to look something pretty close to that. Okay? And I'm only looking for, actually I only care about, if you notice here, from 0 to 5. Right? So that means I'm kind of cutting off. I'm kind of cutting off here at 5. I don't care about this. I only am going from 0 to 5. Okay? Now we're drawing 5 left endpoint rectangles. When it says left endpoint, that means the height of the rectangle is the left. When the left edge touches the top of the function, that is left endpoint. So when the left edge touches, you move over. If it was the right edge, it would be the right side. And we should have this. So that's A done. That's B done. And then sigma notation. So this is a repeat of our other question. What was it? Question 6. This is kind of a repeat of that. We're going to have a summation. What is, again, like review. I mean, try this by yourself now. What's the argument? Remember, we're adding areas of rectangles. My base is 1. I'm going to write 1, even though like I don't need to. I'm just writing it just to show you the base is 1. And the height is going to be, even though I could write it as square root of x plus 1, I'm just going to write it as f of I start at 0, right? I mean, even though I don't need to, let me just put a 0 here just to show you that's my starting point, 0. And since I'm taking, I'm moving over every 1, it's just going to be plus x. Okay? And then I'm going to go from, remember the first value I want to take is the 0, right? So when I plug in my first number here, I should get f of 0, 1 times f of 0. So I don't want this to be a 1. I want it to be a 0. It's going to be x equals 0 to 4. Okay. And that's it for this one. I mean, again, this would simplify to just summation 0 to 4 of f of x. That's it. It's pretty easy, or pretty simple. I wouldn't say it's easy. And then if I asked you to find the areas of all of these, you would find f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4, right? That would get you the areas of all these, okay? And you plug them in to this and add them up, okay? Last one. Prove that the function f of x equals x squared minus 4x plus 2 intersects the x-axis on the interval 0, 2. Okay, so this is intermediate value theorem, IVT. You don't need to sketch this curve. You don't really need to you don't need to really do anything with this specifically, but you do want to find what is f of 0 and what is f of 2, because you want to know where this starts and ends. Okay, so f of 0, when I plug in 0, I get 0 minus 0 is just 2. When I plug in 2, I get 2 squared minus 8 plus 2. So that's 4 minus 8 is negative. 4 plus 2 is negative 2. That means, just visually, right, we're going from 0, 2 right here to 2, negative 2. Look, what's happening, right? What are we doing here? We are intersecting the x-axis. Right here we have to, right? So what I'm looking for here, this is good, right? What I did here is good. What I'm looking for is, since x squared minus 4x plus 2 is continuous, and f of 0 equals 2, and f of 2 equals negative 2, and 0 falls between 2 and negative 2, f of x must cross the x-axis. Okay? So these are kind of key parts. It's continuous, right? This function doesn't have any holes or anything, does it? Right? It's not going to break at any point. And my interval, right? My interval is this point right here, from 0 to 2. Since f of 0 is 2 up here, and f of 2 is negative 2, and it's continuous, therefore we must cross the x-axis. So I don't think I'll be like that nitpicky about this on the test. What I'm looking for is you mentioning that it's continuous, you mentioning that it's basically it's crossing the value that I'm looking for, and that's it. If the value that we want is in between the two values that it goes between, then it must touch it. That's it. That's the practice test.